Thank you, Jens and Julia. This is a very lovely colloquium so far. I'm glad to speak here. And I'd hoped, of course, to speak in person because this is my sabbatical year, but this is at least better than not seeing you at all. So my talk today is on joint work with Laura Skoll from Fort Lewis College in Colorado. And this has been an ongoing project for a number of years. It started out with a group of female graduate students at the Banff Institute for International Research in Mathematics. And so at that particular project, we mostly worked out examples, and I hope to show a couple of those at the end as well. But I'll start by telling you what Orbispaces are, and then we'll talk about what morphisms between them are, and then we'll get to, hopefully, our mapping objects. And the importance of them is really in homotopy theory, in being able to talk about path spaces and other related objects. And then I'll talk a bit about the properties of the mapping objects, that they have the categorical property of being exponentials, but they can also be seen as giving enrichment. Again, the categorical version of enrichment, which is the idea of, you probably have seen this for topological spaces, that we can give the mapping space, well, you can think of the set of maps between two topological spaces, but you can also think of it as a space by giving it the compact open topology, and that actually would make it an exponential in topological spaces. So we want to do things like that for Orbispaces, and Orbispaces are defined like manifolds, but they are allowed to have some mild singularities. So let's go have a look. So Orbispaces were originally introduced by Setake in 1956 as Hausdorff spaces. I think Setake asked that they be, I have a couple of additional properties, but I'm just asking for Hausdorff spaces right now, with an atlas of charts that will describe the local structure. And so that local structure, as you can see in some of my charts here, can be nice and smooth, but it could also have some cone points, as in this chart here, and other features. So we'll go on to give some examples of that. So in particular, if I look at two-dimensional orbifolds, the local charts would be open subsets of R2, and we would have, what we're allowed to have besides the open subsets of R2 is an action on those charts. And so, for instance, it could be a rotation, it could be an action by reflection. So those are finite actions and would give us points with finite isotropy. So, for instance, this point here, the cone point, would have an isotropy group of Z3, and the points on this reflection line would have isotropy group Z2. Let me see. Okay. So then what we require then is that the quotients of the charts that I just described, so the quotients by the action of the group would be an open subset of the space. So if we had a rotation by Z6, for instance, then you would get a cone point like this. And so if you look at orbifolds with smooth structure and with distance and so on, you would actually be able to get that information also by looking at how distance develops in the space. However, we are not going to do that. We're not requiring right now that we actually have like manifold structure necessarily, or smoothness, and that's why we call them Orbispaces. So in our case, we have to explicitly keep track of what those isotropic groups were and so on, so in terms of charts. And Oh, wait, that went too fast. Okay, here we go. So what we do have, aside from, so we'll think of an orbifold really as a space with the atlas, and those atlases need to satisfy a bunch of properties in terms of local compatibility and so on, and are actually rather painful to work with. So I'm only giving it as the motivation, but next we will introduce Orbispaces with a different mathematical concept to be able to work with them. For instance, describing maps in terms of atlases is a real pain. And Satake's first two papers actually give two different notions of maps. And neither one was in the end the one that people actually wanted to work with. And it's because it's so hard to describe maps correctly in terms of atlases. So we will be doing that in terms of groupoids in a bit. I want to just mention one other thing, and that is that every orbifold can also be described as the quotient of a space, a Hausdorff space at least, and then you may want to ask some extra things, but by the action of a compact Lie group, and where we only require that the isotropic groups be finite. And that's a fairly recent result. And so you can now also describe maps in those terms. I will not be doing that today. Our notion of groupoids that we're going to work with is still fairly close to those atlases. So we'll see that in a bit. So here we go. I'm going to just give a couple of examples. The examples will be mostly in terms of more global group actions, and just because they come with nice pictures. So we can, here we have the action of, this would actually be Z2 star Z2 acting in one direction, and then another is also in orthogonal direction on the plane, and the two actions are commuting. So we would have the reflection lines like this, and then the opposite ones, orthogonal ones here. If you now look at what is the underlying space, you would just have to take a fundamental domain, as I indicated here, and each of the corners you would have a Klein-Vier group acting, and along the edges we would have Z2s acting, and that could be described also in terms of local charge, as I kind of indicated here. So your local charge around the corners would have that Z2 action in two directions, and along the edges you could look at charts that have just the reflection. Here's another version of a billiard table, where the reflection lines are now coming together in at different angles, giving us dihedral groups of order 6, like that. And so here you would have a corner where the local action would have been along reflection lines like that. I'm going to come back to those in the end. What's the important difference for us today between these two is that in the first billiard table, here we go. Oh, oops. Good. Here the Z2s in the corners are not conjugate to each other, and here they will be. So here they are, and that will make a difference for their mapping spaces in the end. Okay, so another fairly simple orbifold is one that we can get by the action of Z2 on S1 by reflection. And the underlying space would, of course, just be an interval. But the endpoints are special because they were coming from an action by reflection, and we call them often silvered endpoints. And so we want to keep track of that structure, the Z2 structure there. If you were doing this in terms of atlas, I decided to write it down here. So the underlying space is really just a black space here, but I've indicated how the different charts lie on top of it. And so we would have a chart which is at 2 action, the green chart giving the left side, the orange chart giving the right side. The purple one would kind of cover the part that doesn't have any singularities, and I would need small charts to say how those charts connect to each other. So the blue and the red chart are still just trivial charts, but giving the indication of how the charts relate to each other. And we see that we have 2 inclusions of the red chart into the orange one, because the action takes the one inclusion to the other. So just here you see a little bit of how that works out with the compatibility conditions between the charts, which I won't talk about. Okay. Oh, sorry. I have to get used to the lag here. So the Teardrop Orbifold is another one that is often used as especially a good counterexample for lots of things. And it's really like a sphere, except there is one special point that is obtained by a rotation action. I took Z2 here. And so we cover the top by this chart with the rotation action, and the rest of the teardrop can be covered by charts with trivial groups. So as I said already, atlases can get complicated, maps between them get even harder. So in my thesis work with Ike Moerdijk, we introduced a different way of looking at Orbispaces and in terms of groupoids. And so for my groupoids, I am going to keep track a little bit more of, generally, most of the time I will just work with G0 and G1, just like Marina was doing. But we do want to keep track of the fact that we do need to have that space of, which would be, so the G0 are the objects of my groupoid, G1 are the arrows. And in this case, rather than just having sets, we'll have spaces there. And then there's also needs to be a space of composable pairs of arrows. So this is the pullback of source and targets over G0. So now, of course, we don't want to use all groupoids. It turns out that you can describe Orbispaces by using proper etale groupoids. That means that the source map is etale, and because we're working with groupoids, that means the target and the units and the inverse and the multiplication will be etale as well. So etale is that the map is a local homeomorphism. And so for every point in the domain, there's a small open neighborhood so that the map restricts to a homeomorphism on that part. And we ask that the combined source-target map be closed with compact fibers. So those are the 2 properties, and I'm going to show you a couple of examples and then we'll get the idea there. Okay. First of all, if we have a discrete group that acts on a space X, there's always what we call the translation groupoid or the action groupoid. So we would have as a space of objects just the space X itself, that's indicated here. And then for the space of arrows, what you would get is a bunch of copies of X, and you would have a copy for every element of the group. So let's say for the identity, for G1, for G2, etc. And the source map would just be the projection down to X, and the target map would give the indication of the action. So let's say that G2, so here I can think of this as an X, G2, and then so the source of that would be X, and the target of that point so would be here with what would be G2 times X. And the multiplication in this groupoid would be given by the, so the composition in the groupoid would be given by the multiplication of the acting elements. Okay, so let's actually see how that works out for an orbifold. So we had S1 with the Z2 action, and then its space of objects will just be the circle, and the space of arrows will be 2 copies of the circle, and so the sigma copy and the E copy. And for the E copy, the source and the target will just be the direct projection down. But for the sigma copy, because the reflection was like this, the source will be right below it, but the target will be obtained by the action. We'll have a couple more examples coming in a moment. A morphism between groupoids is normally the internal version of a functory between groupoids. So you would expect a map on the objects, a map on the arrows, and then you need to make sure that all the properties are respected. So source, target, units, and multiplication. And if you want to look at the composition, then we need to require that this diagram here commutes. Now, of course, because we're inside tuple spaces, this means that phi naught and phi 1 themselves need to be continuous. So now let's look for a moment, because we will see that that's not entirely enough for what we want between Orbispaces. So I'm going to give you a different presentation of that silvered interval, or interval with silvered endpoints. I'd given it as that action groupoid with a circle, but I could also do it in terms of the atlas. And what I do in that case is the space of objects. I just need to take enough charts out of my atlas so that I cover the whole underlying space. So I took from earlier that green chart, the orange chart, those were the 2 endpoints covering, and then the purple one for the middle. Now when I look at the groupoid, I am going to need to use all the other charts to give the correct arrows between them. So first of all, for over the green part, I would need the action groupoid for Z2 on that part, and same thing for orange. Then I need some, so over the purple part, of course, I need the identities, but that's all I need there at first at least. But then I have to include some pieces to the in the space of arrows to indicate that the end parts of the green chart are connected to the end parts of the purple chart here. And in order to do that, I have 2 blue pieces here, one to give the arrows to go from here to there, and one to give the arrows from there to there. And the same kind of thing works for the purple. And then also this will automatically make it possible to compose arrows in the space of arrows. And the same thing works on the other side here. So we see that this is a very different kind of groupoid. It has lots of connected components. And if I try to see whether I can go between these groupoids, so they're representing the same Orbispace, and I would hope that they will be isomorphic in my category, or at least equivalent, if I'm looking at a 2-category or a bicategory. And I see that, well, I can make a morphism going this way, as I have indicated with my colored stuff here. So the real groupoid here on the right-hand side is just the black circles, but I indicated with the colors how I would map the left groupoid to the right groupoid. And so that's possible, but going back won't work because I would have to break spaces, and we don't do that in topology. So we have to look a bit more carefully at what kind of map is this. It's obviously not an equivalence yet, but it is what we call an essential equivalence. So let me tell you what an essential equivalence is. So a morphism between internal categories, really, but today internal groupoids, is an essential equivalence when it carries the kind of structure that we would normally call essentially surjective and fully faithful for functors between categories. But we need to suitably topologize those notions, so we'll look into that a bit more carefully. So essentially surjective normally means I can reach every object up to isomorphism. So I can reach an object, I might not reach the object itself, but I can reach somebody who's isomorphic to it. And so if I draw that in a diagram, because I'm working with groupoids, I just have to require that if I want to reach everything in H0, I just have to make sure that if I look here, I take an X, I get to phi naught of X, and now here I might have an arrow from phi naught X to somebody else. Then I know that because this arrow is always an isomorphism, it's a groupoid, I can reach Y, so to say. So I have to ask that if I look at the pullback here, which is those points X, comma, H, if I call this H at least, I need to make sure that this map is surjective. That would be kind of just checking, okay, in sets, in ordinary categories, that's what we would require. We'll have to be a little more careful here because we're doing topology, and we will ask that this actually be an open surjection. So we ask for a little more than just surjective. We ask that this map be an open surjection. Now, because my groupoids are all etale, so this doesn't work in general, but today, because we're working with just etale groupoids, so S and T are already open maps, the openness of the surjection is equivalent to phi naught being open. So I can also ask that that map on the top is surjective and phi naught is open. That will give me the same result. So that's the first part. That was essentially surjective. To be fully faithful, I really ask that the local structure in the two groupoids looks the same. So as far as the arrows is concerned, and there's a nice categorical way to say that, namely that this square be a pullback. So if I have points X and Y here, and I look at phi naught X, phi naught Y, then we see that the arrows between X and Y in G1 correspond just exactly to arrows between phi naught X and phi naught Y. So, and again, this is the good way to say topologically, in the sense that all the maps here are continuous, and this is a pullback in spaces. Good. So if we are essentially surjective and fully faithful, we call a map an essential equivalence. And if we would go back to that example we had earlier, here. Okay. So this map, we see that if I look at what's happening between 2 points, so you might be wondering, now, what about a point here and a point there that corresponded to each other? They would have just one map here, and here they actually became the same point, so the identity sits between them, and you do actually check the whole thing, you do get that pullback. And it's also clear that we are open, because these were all open intervals being mapped into the circle. And if I look at any point that I haven't reached in this black circle, you might be thinking here, well, that is isomorphic to a point that was reached. So we are also essentially surjective. So this works here. Okay, so my essential equivalences are going to become my equivalences. So I want to study a little bit more about what do we know about them. Turns out they are closed under taking pseudo pullbacks along arbitrary maps. So if this is an essential equivalence, epsilon prime will be 1, 2, if this is the pseudo pullback. they're generally not closed on the pseudo pushouts. Actually, pseudo pushouts are bad for orbifolds. Generally, you don't take those, except when you have both of the arrows being essential equivalences. So if both epsilon and delta are essential equivalences, you can take the pseudo pushout. And if these were they were groupoids representing orbifolds, so will Q be still. And then everybody is an essential equivalence here, which is convenient because you might be asking yourself, okay, what does the equivalence relation look like on the collection of all Orbispaces? I mean, a priori, the definition has to be, well, two orbigroupoids are Morita equivalent if there's some zigzag path of essential equivalences between them, and that could be very unwieldy. However, because we can take either our pullbacks here and end up with a short path of length 2, so we can either say, well, okay, they're Morita equivalent if there's a span of essential equivalences, or I could take those pushouts and it would tell me that they are Morita equivalent if and only if there's a cospan of essential equivalences. And that can be very convenient when you want to show that particular properties or particular characteristics that we're going to describe are invariant under Morita equivalence. And I won't go in detail today, but there is also a description of Morita equivalence that generalizes the notion clearly from rings, and so the idea of modules between rings, that this is a generalization of that as well, although I won't spell that out. Okay, so I want to invert these essential equivalences to make them equivalences, and I need to use for that a category of fractions. I have made some extra slides to explain that. Maybe I should ask my audience quickly, is it helpful if I start for a moment at fractions of a ring and show how we get to fractions for a category and a bicategory? Would that be something that is good to kind of go into? Maybe some other questions as well. I'll take a moment to take questions.
May I?
Yeah.
This is very stupid, I think.
There are no stupid questions.
No, but you say that that you can like view these orbifolds, Orbispaces as this kind of groupoids.
Yes.
Just to understand things a little more. What about a normal, regular smooth manifold? Then what happens in that case? I mean, since.
Oh, excellent. That's actually a great question, and I should have put that example in. So thank you for asking. So there's two things you can do to make a manifold into a groupoid. And that also will indicate how there's two canonical ways to turn orbifolds into groupoids. So manifolds, if I can just take it as the groupoid with the space of objects being the manifold itself, and the space of arrows being also the manifold itself, and take all the structure arrows to be the identities. This is the kind of silly way to do it, but it is something that makes sense in the following way. I'm just going to scribble here. So I can take my manifolds and then just say source and target identity, and I take M again, because these are just the identity arrows on M. And so in that case, sorry, that should be that way, the unit and so on, all identity maps. So that's one way you can do this, and this is generalized to orbifolds in the sense that if I describe an orbifold as a space X with just one group acting on it, like that compact Lie group I talked about, then the groupoid for X would become the G cross X, the action groupoid I talked about earlier. So the action group could reduce to this M with identities version. the other, perhaps more interesting one is if I have given M by an atlas, then I can take as a space of objects the disjoint union of my atlas charts, let's say UIs. And in that case, for the space of arrows, I need to, of course, indicate everything. How the compare the transition maps are going between the charts. So I would get something depending on how you have done things. I'm writing it as UI intersected UJ. You might want to possibly be a little more careful. Take its pre-image in, well, so I take the intersection in the space and then take it back into UI or UJ. But basically, this is the idea. So you have, and this source and target would give me then the transition maps between UI and UJ. And so the source would go into UI, the target goes into UJ. And the further on for the composites, you would get the triple intersections. Does that help?
Yeah, sure. Definitely, thanks.
Any other questions?
Dorette, these two presentations then would be essentially equivalent, I guess.
Yes, correct. Actually, that's a very nice way to look at it. Thank you for asking that, because I can now, again, I can make a map from the disjoint unit of UIs into M, but I cannot go back directly. So, but again, this is an essential equivalence because it covers all of M, and the local structure is still that 2 points in the disjoint unit of the UIs are getting exactly one morphism between them, if and only if they go to the same point in M. So.
Okay, thanks.
Good. I think I'll just quickly look a little bit at localizations. Oh, wait, that's the wrong one. Oh, wait, here it is. Good. So here's first a quick reminder about the OR conditions for a ring of fractions. So if we have a ring with units and a subset that of elements for which we would like to turn into units, so turn into elements with a multiplicative inverse, we require usually that one is in S is multiplicatively closed. I see I can't spell that, but that's okay. So by the way, the OR conditions are not necessary. They're sufficient. I want to stress that because I'm going to chisel a little bit at them later. And if I have an element A in R and an element S in S, then I can always find, and I'm going to write this right now as arrows, even though they were just elements, but let me write them as arrows. So we have an A and an R, and so in S, sorry, S is an S. Then what this is saying is that there is an S primed in S and an A primed in R, so that this commutes, so to say. So I'm just thinking of ring as being a one object category. So S primed A is equal to A primed S. So that is the left OR condition, and then if we have and for all S in S and A and R, if I can multiply them to become 0, then in this order, then there's another element in S so that I can make it 0 in the other order. And in that case, if you can do that, the localization is given by these pairs, where SA is equivalent to S primed A primed if there's a T, so that's the, when I compose multiply the difference like that, then get 0. So I think of SA as A over S, and that's why it's called fractions. And this is how you make the rationals out of the integers. Okay, so now we want to do this for categories. And so I'm still asking then that identity arrows are in W. So that was where 1 was in W before or in S before. And we asked for W to be closed on the composition. Strictly speaking, that's not entirely needed. That's why I said it's sufficient conditions, not entirely necessary. And if you want to know exactly what is needed here, read my most recent paper with Laura. For each cospan, as before, except I had it as A and S, we have now written it as a cospan, and we require that there is a commutative square, just as I drew it for you before. And the condition about being equal to 0 has to change a little bit. I can't ask that WF minus WG is equal to 0, but I'm just going to ask that they be equal. So if WF is equal to WG, then I need to be able to make them equal on the other side. So I need to be able to put V on this side and make them equal that way. So that is what the 0 condition turns into. So this was for categories. That was done by Gabriel and Zisman. And so now, and if you have these conditions, the localization by fractions is still by pairs, but the way that, so we had an equivalence relation on our fractions, and now the equivalence relation on the fractions here, on those spans, becomes like this. So two spans are equivalent precisely if there are arrows U and U primed, so that the composites here are in W, and this diagram commutes. Okay. Now, when we go to two categories or bicategories, which we want to do for our orbifolds, we are going to put some two cells in here. It will be, the left-hand side will be asked to commute, and on the right-hand side, so because we're going to make them into cells, we're going to have two cells. We saw that for the localization of a category, we had the equivalence relation on the arrows. What we'll see in a moment for a bicategory is that the equivalence relation will be on the two cells. So first of all, what are the conditions? Still all identities in W, and W is closed on the composition, except that this could be weakened. We also have to ask now that if we have two arrows that are isomorphic by an invertible two cell, then one is in W if and only if the other one is in there. And for each cospan, as before, now we don't ask that we have a commutative square, but we ask that we have a square that commutes up to an invertible two cell. And then again, so this is the OR condition now in a two category. And what we had before about WF is equal to WG, now ask that if there is a two cell from WF to WG, then there is a V in V that we can pre-compose with, and a two cell such that W alpha, and so first of all from FV to GV, and such that the two cells are compatible in the sense that if I have the full diagram with the V in front of it, then I can either look at W, wait a second, that should have been W beta, I just realized that, and is equal to V alpha. Bound to make a mistake somewhere. And then finally, there's a bit of a compatibility thing about the two cells. If I can make two cells equal by post-composing with something in W, then I should be able to make them equal by pre-composing with something in W. So those are the conditions. And if my class of arrows satisfies these conditions, then the bicategory of fractions has now the spans as we have seen them before, as its arrows, and the two cells are going to be equivalence classes of diagrams like what was the equivalence relation becomes an representative for the two cells, and there's an equivalence class on these, but I'm going to come back to that once I continue on in my orbifold slides. So I'll get back to those. And wait, find the right slide again. Okay, here we are. So as I had said just before, so first of all, the class of essential equivalences admits this kind of bicalculus of fractions. It satisfies all the conditions. And so that means that the arrows in my bicategory of fractions will be these spans. But now look, I am going to do something that I didn't tell I was allowed to do. So I'll talk about that in a moment. I'm going to say my two cells are just diagrams of this form. I know that I can take a pseudo pullback. So I'm choosing a pseudo pullback for every pair of essential equivalences with the same codomain. And my two cell diagrams will now just be the pseudo pullback on the left-hand side and then an arbitrary two cell from phi p to phi prime q on the right-hand side. And so I need to talk about that a little bit. So normally in a bicategory of fractions, two cells are given as equivalence classes of diagrams, as I had said. So here is my isomorphism, and here's an isomorphism. These are just going down. And so they're equivalent if I can find an S and a T that connects the center objects there in the two diagrams. Sigma and tau are isomorphisms, and such that if I would make this into a very lovely three-dimensional diagram, each one of the chambers in this diagram would commute, which really means that if I compose, I think, sigma with gamma and alpha with tau, that I would get the same result. And if I compose sigma with delta and beta with tau, I would also get the same result. Now, essential equivalences are extremely nice. They're so nice that if I take any choice for an alpha here, there is, for every two cell that there exists between the pair WF and W primed F primed, there's precisely one beta so that the pair alpha comma beta represents that two cell. So that means that I can choose upfront for every pair W primed with the same codomain a square that I like, and then I can just say I take two cells that are represented with those squares. And I don't have to look at equivalence classes anymore. And so I took the pseudo pullbacks because they're particularly nice, and that way I know really what I'm working with. But there might be reasons for taking different things sometimes. So, but just to let you know, if you're looking at essential equivalences, you can choose your squares up front, and then you don't have to work with the equivalence classes anymore. Okay, so normally there are all kinds of issues because two cells, a particular two cell might not be representable with an alpha, or you might have more than one representation, but so we don't have to worry about that for essential equivalences because they have a couple of extra cancelability properties that we normally don't require. So let's continue on. Good. So there's only one problem. If I have a particular groupoid G, there is more than a set worth of essential equivalences moving with codomain G, which means that the home groupoids in the bicategory of fractions would not be small. And so we don't want that. And so we're going to have to look for a smaller class of arrows so that we end up with sets over any given groupoid, and so that so that the bicategory fractions is still equivalent. So the subclass I'm going to be using is also nice because they're much more concrete. We can see what we're actually doing here. I normally think of etale groupoids as the groupoid representations for an orbifold that are closest to the atlases. And because you can think of, okay, my space of objects might have been made out of those atlas charts, and the space of arrows is just made out of embeddings between them. And so in order to keep things small, the only thing I have to ask for is that whatever covering I take for my groupoid must be non-repeating, because otherwise you can still make things big. So an essential covering map for a groupoid G is going to consist of a collection of open subsets of G naught. It doesn't have to cover all of G naught. It just has to cover it has to meet every orbit. And so then I can take the disjoint union of that cover, and I can just map that into G naught by taking the inclusion on every component. And then, so that would be my epsilon u 0. And then this map will be open. It will also be essentially surjective because it was meeting every orbit. And then I can just make sure that I take the right space of arrows by taking the pullback. And that way, the combined maps here, epsilon u 0 and 1, give me an essential equivalence of groupoids. And it turns out it's enough to only look at these guys. Because the problem is really that if you go from one etale groupoid to another, what you need to be able to do is to break things up. And this is precisely what lets you do that. So the technicalities about this are that, well, first of all, this class is small because, or at least small over any groupoid G, because I'm working with a subset of the power set, really. And the essential equivalences are what we call weakly initial among all of the, sorry, the essential covering maps are weakly initial among essential equivalences, in the sense that any essential equivalence can be precomposed with another essential equivalence so that the composite is an essential covering map. And that is enough to obtain an equivalent calculus of fractions, well, an equivalent category of fractions. Of course, we had to also prove that the essential covering maps still satisfy conditions. They're not close on the composition, but they're close enough to that. So what we have is that if I have two essential covering maps, I can pre-compose it with another map to make this an essential covering map again, and that is sufficient. So what we'll be working with now is just the category of spans with the left-hand side an essential covering map. So now I said I would like to work with mapping objects, and I'm thinking of things like path spaces and so on. So the question is then, categorically, what is the kind of thing that you should ask from a mapping object? Well, on the one hand, we can ask that it be an exponential, which means that if I have two Orbi groupoids K and H, if I make a topological groupoid, let's say square brackets KH, then it is an exponential if I look at the categories of generalized morphisms G cross K into H and the two cells between them, and I look at the category of maps from G into this mapping groupoid and the two cells between them, that those are equivalent categories. So this is kind of a right adjoint to the product. I can also ask that there be bicategorical enrichment. And so that's the composition on the mapping spaces would be a morphism again. So the first one determines your mapping object up to Morita Equivalence if it exists. The second one could in principle have lots of solutions. I mean, you could just make everything discrete or indiscrete and it would work. But of course it would be nice if the one that works for number one also works for number two. Now, just to give you a quick view ahead, if you ask here that this be a map between just a functor of topological groupoids, that is not going to work. But if you ask for it to be one of those Orbispace maps where I'm allowed to break things up and then go forward, then it is possible. So we'll see that what we are defining here in a moment is going to give me bicategorical enrichment as long as this is a map of Orbispaces where I have this span. So quick overview of the literature on this topic. Wei-Min Chen asked the same kind of questions in 2006. In his introduction, he says that it would be nice if this could be done in terms of groupoids, but he doesn't do it in terms of groupoids. He has a couple of different representations of orbifolds that he goes in between, and it's closer to working with atlases, and it's because of that very hard to follow because there's a lot of bookkeeping that needs to be done. So our first goal was really to rewrite his paper in terms of groupoids, which we are accomplishing here. One of the things that Chen cannot do is to get the enrichment. He notices that there's an enrichment in terms of the quotient spaces. So if you take the quotients or the underlying spaces of the mapping groupoids, then he gets that composition is continuous. So in that sense, we're able to improve on his work, and we're able to do this now completely in terms of groupoids. Dave Cartridge and Virang Nui are doing it more generally for stacks. They're not worried about enrichment, they're just looking at exponentials and in a bit more general context. And so the results for stacks are kind of, they partially overlap with the results for orbifolds, but in some sense you can do better things for orbifolds than you can do for general stacks. So now just to go back, if we were working with just topological groupoids, then we could give the functors, the continuous functors between two groupoids, a topology with using compact open topologies, and we would get a lovely mapping groupoid. Everything would work without any problems. And that mapping groupoid is also giving enrichment. So topological groupoids are enriched over themselves. And everything is good, or at least if your spaces are, well, okay, if your spaces are paracompact and locally compact, then the result, of course, isn't. If you're working with compactly generated spaces, then you could be completely compact closed. Now we want to transfer the topology that we know for topological groupoids to the Orbi groupoids and their new maps. And together with Pablo Bustillo and Martin Zilt, we have proven that if you look at the bicategory of fractions, the local, so the Hom sets or Hom categories form a two-filtered pseudo-colimit of the categories of arrows and two cells in the original bicategory that you started out with. And so we could then say, well, let's take that two-filtered pseudo-colimit inside the category of topological groupoids. And if you do that, I will say a little bit about that later on how you do that, then you get a result that will give you so we would be taking a pseudo-colimit of, so if we're looking at OMAP from K to G, and K is, I'm here now assuming K to be compact. If you take the colimits of a GMAP, and then so now we have to look for all the groupoids that come from a covering of K. First of all, I will want those coverings to be finite, and I'm also going to ask in a moment that K be locally compact and paracompact so that I can make some good covers. That's going to come up in a moment. So, but if you do that, you can create you get a topology for this one here that is satisfying the properties that I need for an exponential. As I said already, well, actually, you could do the pseudo-colimit even if K is not compact, but the nice results are only when K is compact. So I'm not asking that the groupoid itself is compact, but that its quotient space is compact. And then, and as I said already, in that case, it's also enough to ask that U to be finite. So I get an exponential in the following form that satisfies this property. I'm not going to describe it to you because I have a better one coming up in a moment, and that is nicer. The problem with this one is that the groupoid I get here represents an orbifold, or at least a generalized orbifold, but it's not etale. It is proper, but not etale, and we really would prefer to have an etale groupoid there. So what we have to do is to further cut down on the arrows that we're actually using. So make the space of objects yet smaller for OMAP. And so that it does become proper and etale. And the motivation, or kind of the inspiration for the correct notion of map, came from Chen. Our admissible maps are not entirely the same as his, but they're inspired by his. So we'll still call them admissible. So we will call a span admissible if the collection U is such that all the elements of U are relatively compact in G0, so their closures are compact. That's what Chen asked too, but Chen also asked that his covers be closed on the intersection. We don't have to do that. So we just need closure compact, and we require that the map psi going out can be extended to those closures, and then of course they are uniquely extended. So in some sense, we can think of our spans as being spans like this. So spans that are defined on the closures. Just be slightly careful because this here is not an etale groupoid. So strictly speaking, that groupoid is not sitting entirely inside the category we were looking at. But what we're actually doing is that's why I said we use the admissible maps where we have to correct groupoids, but you can think of them in this way. So we write a map for the full subcategory of OMAP on the admissible spans, and we only use finite coverings, of course. Then in that case, we have to still ask, okay, how do we put a topology on this? And so you could think of, oh, well, a map is a subgroupoid of OMAP. So I take the subspace topology. That is not the one we want to use because it's not giving us the right results. there's another way of making an essential equivalence, and that is by shrinking. So we're going from OMAP to AMAP by choosing a shrinkage for every essential covering that we were using for arrows in OMAP. And so once you have chosen your shrinkage for each covering, then we can send the map epsilon phi to the restriction to its shrinkage. And so then, because this was epsilon was originally defined on something bigger, it automatically has its extension to the closure and for phi as well. So that's where we get then. And so then we can now put the topology on there. So what turns out to happen is when you take that pseudo co-limit is that we basically have no topology, or at least discrete topology, on the epsilon u's. So the left-hand sides are just indexing things. The right-hand, so this is, the left-hand side is almost like considered like a set, and we give it a discrete topology when we put the pseudo co-limit on this thing. And so we are getting simply the G-map on the K upper star U bars, so the closures of the opens. So now we take the compact open topology on the mapping spaces from K upper star U bar to G. And so this is just a disunion of those. And but be careful. So the essential covering map, the covering needs to happen on U, but we take G map of the U bars. And then we continue on with next. The points in the space of arrows are diagrams like this, as we had talked before. The idea is again that this part is just indexing, and so we get a disjoint union for A map K G1, a disjoint union over the epsilon U, epsilon V pairs, and then I just need to topologize the triples phi, beta, psi that fit on this side. So on the right hand side. And so you do that by taking the pseudo pullback of G map K upper star U bar G. That's kind of like, this is looking at the top part here that goes here, and then the bottom, the psi, is sitting here. And then what I want here is the maps from this groupoid to that groupoid, so that okay, this is just the maps from this groupoid to that groupoid. Now, if I take a phi, if I precompose with pi u, then I end up in the corner here, and the same thing with the psi. If I precompose with pi v, I end up here. And if I take the pseudo pullback of these groupoids, what we see is that we get, for the space of objects of Q, we get a point in the space of objects here, which would be that the psi. We would get a phi from the space of objects from this part, and we need a two-cell between phi composed with pi u and psi composed with pi v. This is how a pseudo pullback is calculated. It's an object here, object there, and an arrow there between the images, which precisely gives me that beta. So if I take the space of error of objects of that pullback, I get precisely what a space that encodes the right-hand sides here. So that will give me a map. And I am just wondering, what time did you want me to end? Because I think we're getting there, or I should probably have run over already. Julia?
Yeah, if we can start wrapping up, it would be fine. But I mean, You just went 5 minutes over time so far, so it's fine.
Okay, I will just wrap up then.
Okay,
Thank you. So I've given you the construction. Let me just quickly give you a couple of features of it and one cute example. So first of all, it does give me the enrichment I want. This groupoid is proper and etale. And also the construction is Morita invariant, in the sense that if I work with Morita equivalent groupoids up front, the results will be Morita equivalent. And the same thing is true for AMAP, by the way. It's true for OMAP, but also for AMAP. And so if you're wondering about enrichment, let me just warn you about one thing. If you just take strict composition going across, that won't work. That won't be continuous. But there is a way of breaking it up by the particular atlases you might like to work with for the top corner. So if you compose two spans, you would have to make this span to cover the middle. And there's a way of encoding these W's in a compact open topology opens so that I can just group my families of spans according to which W I want to use for the composition. And that gives me a generalized map from AMAP cross AMAP to AMAP that way. So it works as long as we use Orbigroupoid morphisms. And so then the last thing I want to say is, one sec. I want to give you a nice example of I am going to go, okay, here we go. If I do the rectangular billiard, I might ask myself, what are the Z2 points of this Orbispace? And so those are the maps from the groupoid with just one point in the space of objects and the group Z2 in the space of arrows. And it turns out that we get in intervals with silvered endpoints for each one of the sides of the table or the square. And but there's an extra Z2 acting on this ineffectively, and there's a full Klein-Vier at the endpoints. So it's kind of like an interval with silvered endpoints, but there's an extra Z2 that's acting on the whole thing. So that's perhaps not too surprising. And the reason that these guys don't talk to each other is because we have an abelian group here. Nobody is conjugate to anybody else. But if you go for the triangular one, now if I go for the intervals, I get my 3 intervals again. But at the endpoints, the sigma that acts here and the tau that acts there, and to make it a fixed point, are conjugate to each other. And the chart actually lets you glue these, so we end up with a Z2 circle. And you can also see this in the wallpaper pattern. If you would look at, I don't know how easy it is to get back to this thing, the first ones. Yeah, here we are. If I look at my first one here, this would give me one of the sides of the table. I noticed that this line never crosses one of the bees or the butterflies. It only sits on the blue bats. Same thing for the other ones. They only stay within one type of animal. If I go to my next slide here, if I make a straight line extending this guy, I see that it's actually goes through all the animals. It goes through the bluebirds, the whatever they are, the stingrays, and the whatever, the orange animals. So you see that that line actually continues on, and so that is actually, this is what is the pre-image of that circle. And there is more that can be studied there in terms of wallpaper groups and so on. But this is one nice feature of the Orbi mapping spaces, and this is part of the inertia groupoids that show some of the further aspects of the Orbi structure. And I want to say thank you. My final slide is far away. Here it is. Okay. Thank you for your attention.